Excuse me. Well, I'll begin with a word of prayer. Heavenly Father, we thank you for this day, and I thank you for this opportunity we have just to meet and study your creation. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. Excuse me. Well, let me begin by deriving the magic formula. We didn't get to that last time, so it's probably worth a second here. So we have e to the ta, right? And to derive the magic formula, basically all I do is to add and subtract minus lambda times the identity. And again, that's all times time. You factor the t out if you guys don't mind. Well, fine, there's a t on everything here. T lambda I, lambda ti. All right, so I've just added 0, right? Then the thing is, the matrix lambda t times the identity, it commutes with everything. So like, one of the identities we had for the matrix exponential doesn't generally follow the laws of exponents. But if the matrix is commuting with the other matrix, then it is true that e to the a plus b is e to the a plus e to the b. Or in this context, we have e to the lambda t times the identity matrix times e to the t times, well, a minus lambda I. All right? And then it's just a matter of proving a little identity that's easy enough to prove that that's really the same as e to the lambda t, the scalar, times the identity matrix. And then that right there foils out into like I, well, not foils, listen to me. It expands in its power series, a minus like so. So this is just the definition of the matrix exponential at play right here. And last time we saw how that can be used to extract higher order solutions from the matrix exponential. But that's the proof of the magic formula, essentially. If you look at my differential equations notes, you'll find a few more steps, but that's basically the heart of it. Let me start with an example. Let us suppose we look at the matrix, let's say, J equals to, let's see here, 0, minus 1, 1, 0, all right? If we look at this matrix, let's study its powers. What's J squared? We got look at that. That's we look like minus the identity matrix. Yeah. So this J is a 2 by 2 matrix whose square is minus the identity. It's like the J you guys use in electrical engineering, right? It's essentially like an imaginary unit. So let's think about this. What's J cubed? It's minus J, right? What's J to the 4th? It's just I again, right? Because it's minus minus J squared, which is minus a minus I, which is 1. So what? Well, let's work this out then. What is e to the tj? Let me point out that we could summarize two patterns here, which is that j to the power 2k is equal to minus 1 to the k times I. And j to the 2k plus 1 is equal to minus 1 to the k times j. All right, that's the pattern. For even powers, you get a plus or minus identity. For odd powers, you get plus or minus j. So when we look at the power series that defines the matrix exponential here, n equals 0 to infinity of t to the n, j to the n, divided by n factorial, well, we can decompose that into the even subseries and the odd subseries, right? So you can rewrite this series as the sum, k equals 0 to infinity, of t to the power 2k times j to the 2k divided by 2k factorial, and then plus the sum, k equals 0 to infinity. So this is just a trick I'm doing right now, guys. But anytime you've got a sum over all integers, you could break it up into distinct cases which partition the positive integers here. Well, non-negative integers, I should say. So I did that, even and odd. Yeah. Obviously, that choice is motivated by the fact that there's obviously an apparent pattern here. Yeah. Namely, that this matrix either goes to plus or minus the identity and plus or minus j for even and odd. So doing that, we can rewrite this as, well, we got sum k equals 0 to infinity. I would remind you, calculus 2 is a prerequisite for this class. So we're about to feel that. We can factor that 2j to the 2k out, although I can't factor the minus 1 to the k out. That's stuck in here. But I can factor the I out. And then plus sum k equals 0 to infinity minus 1 to the k t to the 2k plus 1 divided by 2k plus 1 factorial. I can factor that j out if you think about it, right? Now, I don't think this is your homework problem, but it's mighty close to one. Like I said, I have a few problems in your homework that just ask you to calculate the matrix exponential just directly from the series expansion. That's what I'm doing at the moment. Last time I talked to you guys about how to calculate the matrix exponential through a circuitous, somewhat sneaky path of applying a generalized eigenbasis to the magic formula, and that's still that's a way for sure. But look what we have here. Can you guys recognize what is this? I'll start with this one. This one is cosine. That is the Maclaurin series for cosine. What's the other thing there? Sine. That's right. This is a definition for sine, in fact. If you like, you could use that to define the sine. And so what we have is that e to the tj is in fact just cosine of t times I plus the sine of t times j. So this example is somewhat precious in that it wasn't that hard to calculate the matrix exponential directly. All right. Of course, you could write this out more explicitly. What we're looking at is the matrix cos t. Let's see here, j sine t for my first column, and then minus sine t over here, and cos t over there. So that's actually the matrix exponential here, as it happens. Right. Let me do one more kind of like this. Example 2. So I was trying to put this matrix on like test 1, but I kind of like failed. I was trying to make up something that was n sub k, which was like e sub 1, 2, plus e sub 2, 3, plus plus e sub k minus 1 k. All right. So that is a concrete notation, and this here is an element of. I'm talking about a k by k matrix. Okay. Sorry, I'm an idiot. What happens if you square this thing? N sub k squared. What do we get? So if we were to multiply that out, I'm not sure I want to sign up for this. That's why it was the bonus problem. But I think, well, it wasn't wrong, but I think I should have like made a restriction on n that I didn't, which technically made like 2 cases in the problem or something. Anyway, none of you have come to air your grievance about that problem yet, so I can only assume you didn't notice. Let's see here. So we worked out the product of the matrix units. What was the formula for it? Yeah. So what was what was like EI times EJ? Remember how that goes? So we could do like EI transpose, EJ transpose, and that is, oh, I'm a dummy. What on earth? EJ, I wanted an EKL here. I wanted 4 indices, not 2. Dummy, me, not you. So EJ, EK. I'm just working it back out because I forget it when I forget this. I have to redrive it. This in the middle is just the dot product of the two. So that's a Kronecker delta JK. And so we've got Kronecker delta JK and EI EL transpose, also known as Kronecker delta JK EIL. All right. So what that all means is that basically when you multiply these two, result not equal to 0 if and only if what? J is equal to K, right? Only when J equals K do we get something non-zero. So when you multiply this out, what do you get? Can you see it? What have I done? Let's see here. So this times that, the 2's, they be matching, right? Now this times the first one, 0. But this times that gives me E13, yeah? And then if you can think about the, and let's see, is there anything else for that one? I don't think so. I think that's the only one in that whole mess that it gives you a non-zero result for, right? If you think about multiplying this, the only one of these that gives you a 2 matching here. This 2 has to match that 2, right? The only time that happens is for this pairing right here. That's it. And so then when you look at the next one, E23, it hits the next one I haven't written here, which is E34, yeah? And that produces E24, I believe. Right? And then that one, this one here, it's 0 on the rest of it. And this pattern continues until finally you get to the last one here, right? And this hits, well, this one doesn't hit it. This one doesn't do anything, does it? But the one right before it, which is what? E k minus 2 comma k minus 1, right? That one hits the last one here and gives us an E, there's a plus dot 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 here, E k minus 2 comma k, all right? So that, what does that look like actually? Like, let's just try to like write it out with plus dot dot notation for a second here. So 1, 3, right? So I get 0, 0, 1, and then 2, 4. 0, 0, 0, 1, all right? And so eventually we go here to 0. I'll write the last 3 0. So here's k, k minus 1. Okay, so I've got k minus 2. This is k minus 1, k minus 2 row. There's a 1 here. All right? So the next one up would be this. I don't know if you can see it or not. N sub k, what n sub k is this. So in other words, the n sub k has a 1 on the first super diagonal everywhere. When you square this, what it does is it pushes this band of 1s up 1. Bloop. Now it's on the super diagonal, or like the second super diagonal. See? When you cube it, what happens? Like n sub k cubed, it moves the 1s up 1 more. Listen, I can easily do it for like, let me just do it for n equals to 4, just say I see it like explicitly. I'll just do the 4 case. Which is probably what I should have done from the beginning and just claimed that this holds for k, and you would have believed me, right? But I wanted to give you some indication of how you could actually calculate that if you don't like induction. So here's n sub 4. N sub 4 squared is 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. N sub 4 cubed is 0, 0. I should just write the non-zero things, you know? That would be a lot less. Yeah, why don't I just do that? So there's n sub 4 cubed. Everything else is 0. And then n sub 4 to the 4th power is 0. All right? So this matrix is important. Basically, this is one of the fundamental building blocks of the Jordan form. The Jordan block we talked about last time, basically built from this matrix and the identity matrix, right? In particular, you might notice that the Jordan form, the k by k block with lambda, you could write it this way. It's lambda times the k by k identity plus this n sub k thing. All right, that's actually the formula for the k by k Jordan block. So, continuing example 2, what's the matrix exponential? E to the t times n sub k. What's that? You've got I plus t times n sub k plus t squared over 2, right? N sub k squared. T to the k minus 1 over k minus 1 factorial, n to the k minus 1. And past that, you got 0, right? So we can straight up calculate the matrix exponential for this matrix n sub k. I should probably give this a name. This is the well, I mean, this is an example of, so if you have n to the k equals to 0, but n to the k minus 1 not equal to 0, that makes this n a quote-unquote nilpotent matrix of order k. All right. And you could straight up write the formula, yeah? So I'll just stick with my 4x4 for the sake of not going nuts. But you could easily extract the general formula if you had a little more patience than I do today. And so we got like a 1 t, 0, 1, 0, 0, 1, 0, 0, 0, 1. We get the identity matrix from the first thing, and then we get t's on the super diagonal. And then what do we get on the super diagonal, which is not really the super diagonal. I am just calling it for the purposes of my convenience of exposition today, the super diagonal. Or you could call it the sup. Like, what's sup? You can come up with a more professional sounding name. I'm sure there is a name for it, I just don't know it. So t squared over 2 up there. And what's in the top spot? T cubed over what? 6, right? Because 6 is 3. 3! That was a 3 factorial. Sorry, I'm an idiot. But you already knew that. Let's see here. So there you go. The thing is, if you have something like, e to the, let's say, j for lambda, right? Then that's e to the lambda I4 plus t n4. And that just works out to e to the lambda t times this thing we just wrote up here, all right? By essentially the calculation I did at the start. So to find j4 lambda, e to the j4 lambda times t, of course, t. Keep forgetting my t's, it's not good. All you do is just multiply everything in here by e to the lambda t, right? And that is, by the way, reproducing the generalized eigensolutions we saw yesterday, right? If you think about it. The columns in here are going to be like the first column, when I multiply by e to the lambda t, the first column is like the eigensolution, then the generalized eigenvector order 1 solution, the generalized eigenvector order 2 solution, the generalized eigenvector order 3 solutions are respectively the first, second, third, and fourth columns. All right, but let me stop blathering about that. I could talk about this for hours, but I think that's enough. I think that's enough. So we need to talk about what happens, because I had a precondition to the discussion last time, right? And that precondition was that all the eigenvalues are real. But do all the eigenvalues have to be real? They certainly don't, do they? Like, I shouldn't erase this because this is a good example of a matrix with eigenvalues that are not real, right? What's the determinant here in example 1 of lambda I minus j, let's say? We're talking about the determinant of lambda minus 1. I guess that's a plus 1, isn't it? Minus 1 lambda, also known as lambda squared plus 1, also known as lambda minus I times lambda plus I. As you can see, the eigenvalues here are very much not real. So like lambda 1 is, let's say, minus is I, and lambda 2 is minus I, right? So for a real matrix, and that's what we're talking about in here, we keep it real to start with, but math takes us to other places, right? We can't help it. J was a real matrix, but it necessitates the use of complex math. It's not my fault, it's the math. It did it. I didn't do it. I was keeping it real. So, not my fault. But my point, anyway, is that for a real matrix, the complex eigenvalues, they have to come in conjugate pairs. All right? We've talked about this before. I'm just talking about it again. Complex eigenvalues come in conjugate pairs. So, remember this N matrix. We're going to talk about it again here in a bit. I'm going to show you guys yet another thing we can, it's not matrix multiplication, it's a new thing. A new, what's the word? A new operation on matrices we're going to need. We'll get to that. We'll get to it soon. So definition, if lambda is equal to alpha plus I beta, where alpha and beta are real numbers and beta is not equal to 0, and A is, let's say, a n by n matrix for which there exists, let's say, u1, u2, and you know what? Let me make this easy for me. It's not n by n. We're going to talk about 2n by 2n, just for the sake of my making life easy for me. 2n by 2n. So we'll do u1 through un in the complex n vectors. All right, n complex n vectors. Non-zero. And these guys are non-zero, such that they satisfy the chain condition. In particular, a minus lambda I times u1 is equal to 0. A minus lambda I times u2 is equal to u1. A minus lambda I times u3 is equal to u2. You know the drill. A minus lambda I un is equal to u n minus 1. All right? And I really shouldn't do, I'm sorry guys, well, rats. I don't want to force the size of the matrix to be 2n by 2n. Would you forgive me if I redefine that? Sorry. Oh, I'll do it this way. Let me switch this n out for a k. That'll fix it. I'll put a k here, and that makes this a k, and this is a k minus 1, because I don't want to force us to have it as big as the matrix, because a lot of times we have chains which don't reach the full size of the matrix. Okay. This is a generalized complex eigenchain. So this is a complex k-chain with lambda equals to alpha plus I beta, okay? So since A is real, what can you guys tell me immediately? If there exists a complex k-chain for eigenvalue lambda, what happens if you just take the complex conjugate of that stack equations I just wrote? Like, take the complex conjugate. Think about this. If we just take this mess right here, right? Complex conjugate, what do we see? Tells us that there exists a complex k-chain. Sorry to the people at home, but you chose it. Now you use your imagination. I did write something on the board. It doesn't actually show up on the video. This particular marker is like invisible. So, practically. With lambda conjugate, alpha minus I beta. That's the eigenvalue for the complex k-chain. So if you have a k-chain with eigenvalue, let's say 3 plus 2i, there's a corresponding chain with eigenvalue 3 minus 2i. They always come in conjugate pairs. But the cool thing is, we only need one of the, we can ignore the conjugate chain. We saw this before with the complex eigenvector. Complex eigenvector was this story with k equals to 1, all right? All right, so let's bust out the real and imaginary notation. So like u1 is a1 plus ib1, u2 is a2 plus ib2, uk is ak plus ibk. Now here, the a sub j and b sub j, these are all respectively Rn vectors. They're real. They're respectively the real and imaginary parts, right, of this vector here. All right. So let's look at what that says. So on the one hand, we've got what? We've got AU1 is equal to lambda 1 U1, right? So what is that actually? Like, let's work that out. That tells me A times A1 plus IB1 is equal to alpha. And not alpha 1, that's just lambda 1. There's no lambda 1 here. This is all lambda. So alpha plus I beta times A1 plus IB1, yeah? Multiply it out. What you got? You got yourself A1 plus I times AB1 is equal to alpha A1 minus beta B1 plus I times alpha A1 plus beta B1. All right? So from that, I can read two real equations. I get the real part is equal to the real part. So I get this part is equal to that part. And I get the imaginary part is equal to the imaginary part. All right? So I'll write those over here for good measure. AA1 is equal to, alpha A1 plus, or rather minus beta B1. AB1 is equal to alpha A1 plus beta B1. So we're going to save those for later. Now let's work out the second one. What's the second thing down here? We've got the generalized eigenvector of order 2, U2, right? But now it's a complex generalized eigenvector, all right? So that gives me, if you look at it, AU2 is equal to lambda U2 plus U1, you see? All right, plus U1. And if you work out the calculation, analogous to the one I just did in the black there, it's pretty easy to see that you get almost the same calculation, but you get the following. You get A2 is equal to, well, it's equal to alpha A2 minus beta B2. And you get A times B2 is equal to alpha A2 plus beta B2, right? So that would be all we'd get, right? That would be all we get if it was just this equals that, all right? That would be exactly the same. Yeah, it would be exactly the same, but it's not, because there's that extra piece U1, which adds a plus A1 here and a plus B1 there, all right? And this pattern continues. It continues until finally you get to AK is equal to alpha AK minus beta BK plus A sub K minus 1. And then ABK is equal to alpha AK plus beta BK plus A sub K. Oh, that was K minus 2, my bad. No, K minus 1. Yeah, K minus 1, BK minus 1. I'll get it eventually here, BK minus 1. All right, great. So that, when we study the formulas that we get for the matrix A with respect to the real and imaginary parts of the complex eigenvectors in the generalized eigenchain, those are the conditions we get. So check this out. If we put this all together, I think I can erase it. I think we're going to need that. We're not going to need that, so we'll get rid of that. So the general theme of this week's lectures is trying to understand how to take a matrix and put it into a form which is sort of a standardized form. So we started that discussion earlier with we've had a couple different approaches to this, right? We've had the LU decomposition, we had the QR decomposition. Those are both nice because those you can do even when the matrix isn't square. That's pretty cool. If the matrix is square, we could ask the question, is it diagonalizable? So we answered that question earlier in the course, and the answer is if and only if there exists an eigenbasis. At the moment, we're dealing with the other possible contingent cases, which are, there isn't an eigenbasis, and that could either happen because there's not enough eigenvectors, which we talked about last class, or it could happen that the eigenvalues are complex. And if the eigenvalues are complex, it may or may not be necessary to introduce also this generalized complex eigenvectors. But if you put that all together, that's everything. Like, that will cover every possible real matrix. Every possible real matrix is similar to what's called a real Jordan form. So the real Jordan form I'm about to describe here. So like this, if we let gamma equal to A1, B1, A2, B2, AK, BK, all right? And suppose that, and now I'm going to assume that A is actually a 2K by 2K matrix, okay? Because I don't want to, if this is a 2K by 2K matrix, and I'm saying that these are the real and the imaginary real and imaginary parts of a complex generalized eigenvectors, like I've laid out in the middle board, then what we calculate is that this right here, right? So what that is, if we jump back to my theory, that's the matrix of like left multiplication by A in the gamma basis, right? So what that looks like is you do, like A times the first thing in the basis with respect to the gamma coordinate system, then A times the second thing in the basis times the coordinate system, and then the third column is A times the third thing in the basis, gamma coordinate system, and so forth and so on, right? So the columns of this matrix are informed by these equations over here. Eventually we get to a k gamma and a bk in the gamma coordinate system. And what that looks like is, well, it's kind of a mess to write out in the plus dot dot notation, but I guess I started it, so I'm going to finish it here. So we got a alpha. So like the first column, I get alpha in the first spot, minus beta in the second spot, and then zeros after that. In the second column, I get alpha in the first spot. What? Whoa. Dude. Come on, guys. Don't let me do that. I'm just talking to myself here. Ay, ay, ay. So, multiply this out. What happens? Yeah? A times beta, right? So this is supposed to be a beta here, and that's supposed to be an alpha there. All right? Which means that this was beta, this was alpha, which means that this was beta, this was alpha. Let's see here, finally down to this one, beta. I think I fixed all the offending miscalculations. Sorry about that. You do actually have to like multiply it out, So anyway, the pattern here is alpha, beta, alpha like that. So it zeroes all the way down, okay? So that's the first two. All right? Then after that, what happens in the third column? We get 0, 0, alpha minus beta, 0, 0, beta, alpha. Is that true? I don't think it's true. What have I not taken accounted for? Look at the third equation here, right? We also have a 1 here. Where's that put? What does that do? That puts a 1 first thing in the basis. So the coordinate vector puts a 1 up here, you see? And the next one, there's a 1 right here. That's how that works. And this continues until finally down in the lowest block, you get your alpha, beta, minus beta, alpha, and there's a 1, 0, 0, 1 right there. All right? So if you can imagine this pattern continuing. It's a bit much to write. Like here's the 4x4 case, right? So the real Jordan form, I forget my notation. Well, we can use whatever notation we want. Let's say for, what would you guys want? Do you want the number here to refer to the size of the matrix? Let's make it refer to the size of the matrix. So this is a 4x4 matrix with eigenvalue alpha plus I beta. This is the 4 by 4 matrix alpha, alpha minus beta, beta alpha, alpha beta minus beta alpha. Those are the blocks in the diagonal. And then up here you've got 1, 0, 0, 1. Oh, good. Okay, so there is a, like, I know this pattern's like a bit much to digest, but there's an easier way to look at this if we introduce that new operation I was alluding to. So, look, we can rewrite this as follows. We can actually rewrite this as, oh, I need to, I always, there's like a 50-50 chance I remember what I'm about to write right correctly, so I had to look it up in a book beforehand to make sure I don't do it wrong. So here it is. So there's something called a tensor of two, or sometimes it's called the Kronecker product of two matrices. So A tensor B. The way this works is, maybe I should do MN. It's AB anyway. So this isn't necessarily the same A as this one, is what I'm trying to say. Anyway, so if A is an M by N matrix, it goes like this: A11B, and then A12B, and then so forth and so on. A1N, B, that's the first. So these are all blocks, all right? Down here, you've got A M1, B, A M2, B, eventually A Mn, B. So basically, you just make a new matrix where every block is formed by taking the like the scalar from the matrix on the left and just putting a copy of the matrix on the right. So with respect to this notation, this is the 2 by 2 identity, tensor the matrix alpha, beta minus beta alpha, plus this right here is the matrix 0, 1, 0, 0, tensor the identity matrix. And in fact, this one over here can be written instead simply as the K by K identity matrix tensor with the alpha beta minus beta alpha matrix plus n sub k tensor the 2 by 2 identity. This is a concrete, straight up, that's the formula right there. That's what it is. So this tensor is nice. Now what's the real Jordan form? So the real Jordan form of a matrix, it's basically the full real Jordan form is a combination of what we did today and what we did last time. Because a general matrix, it could have real eigenvalues, it could have imaginary, complex eigenvalues, right? And so what you do is you find a basis of chains, some for the real, some for the complex, and you can build enough of them that you get a basis for the whole space. And if you use such a Jordan basis, a real Jordan basis, when you multiply the matrix by the basis matrix inverse times the matrix times the basis again, it will be, the form of the matrix resulting will be a direct sum of Jordan blocks and generalized Jordan blocks. So let me give you an example of that. I guess over here. Now this is the kind of thing that I don't tend to make students calculate unless they've got computers. Or I just give you information, or it's got to be like really sparse, you know. So here, let me just write one down and we can talk about what it means. So, example, oh man, Then I don't know what example I'm on. Example 4, is it? 2, 3, is it? Example 3. So let's look at something. Let's say A is J3 of 7, direct sum J1 of 7, direct sum the real Jordan form. I'll do a 2 by 2 block of 2 plus I. And then the real Jordan form, I'll do a 4 by 4. That's all I got patience for here. And let's do just a 3I. All right. So how big is this matrix? A 10 by 10? 4. I think just 8. Because we've got 4 here, and then 2, and then, yeah. So 8 by 8. Mostly 0, though, yeah? So the blocks are really all I'm interested in. So we've got a 7, a 7, a 7. 1's on the super diagonal. That's my first. All right. And then J1 of 7 is just a 1 by 1 block. That's just that. RJ2, that's a 4 by 4 block. And here we have alpha equals to 2, beta equals to 1. So I do 2, 1, minus 1, 2, and then 1, 0, 0, 1, and then 0, 0, 0, 0, and then 2, 1, minus 1, 2, and then, aw man, dudes, what did I can't read. 2, right? So it was just this. Sorry. That one was the 4 by 4. And so I've got this one. Notice this one's got alpha equals to 0, beta equals to 3, right? So that gives me 0, 3, minus 3, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 3, minus 3, 0. That is an example of real Jordan form. Now, from this, I can tell you what the eigenvalues are. So this has eigenvalues lambda, lambda 1 equals to 7. Here you've got the, I used M for algebraic multiplicity, right? M1 is 4, but N1 is what? And then lambda 2 is like, 2 plus I. You've got M1 equal to 1 equals to N1, N2 rather, although that's complex dimension. And then lambda 3 is 3I. And here you have M3 equals to 2, but N3 equals to 1. So N was the geometric multiplicity. M, as in mommy, N as in nanu nanu, is the dimension of it's the number of linearly independent eigenvectors, right? So like, I only have 2 eigenvectors for this one, so the geometric multiplicity is just 2, right? So if you wanted to solve dx dt equals to ax, could you do it if you had this? So the question then is, how do we get real solutions from the complex? So like just, we don't have too much time here at the moment, I know, but if you take e to the ta times like the, complex eigenvector, uk, you still get, e to the alpha plus I beta times t, and then you get like uk plus t uk minus 1 plus da 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 plus t to the k minus 1. So same formula I wrote last time, guys. But now, what's the difference? The difference is that those are complex vectors. And e to the alpha t plus I beta t has to be understood as, e to the alpha t times cosine beta t plus I times sine beta t, yeah? And all of those U1 through UK, those are all, they all have, we have decomposed those into like A sub j plus I B sub j, right? So the real solutions, you simply get, so if I say this is Z, all right? So this is like, oh my bad. So if I call this whole thing Z, right? Then the real part of Z and the imaginary part of Z, these are both real solutions. I think we did this before for the complex eigenvector case. My point to you is that same idea holds here, and you just pick off the real and imaginary parts. So something like this is going to give me solutions like, where am I? 1, 2, 3, 4, 5, 6. Wait a minute. Well, you said 10 by 10, didn't you? Oh, you can count, can't you? Yeah, I shouldn't have argued with that. That is a 10 by 10. You should push back. When I say you can disagree, push back, please. It's A15. I need correction. So, anyway, my point is, if we were to look at the solutions that correspond to this, we would get cosine 3t, sine 3t, as well as t times cosine 3t and t times sine 3t times appropriate vectors. I don't think I have time to write that out at the moment, though. So I'll stop there, I think. Oh, man, you guys gotta stop me.